Okay, so this is going to be a new one because we did not talk about this in advanced chemistry. So we're going to talk about significant figures. So significant figures deal with accuracy and precision. And as you can see here, there's varying degrees of both accuracy and precision. For accuracy, right, this refers to the closeness of a measured value to a standard or known value, right? So you're measuring against a standard or known. For precision, this refers to the closeness of two or more measurements to each other, right? So using the example given above, if you wish to weigh a substance 5 times and get 3.2 kilograms each time, your measurement is very precise, but that may or may not be accurate. So a good analogy for understanding accuracy and precision is to think about a basketball player shooting baskets. If the player shoots with accuracy, right, their aim will take the ball close to or into the basket. However, if a player just shoots with precision, their aim will always take the ball to the same spot, which may or may not be close to the basket. A good player will be both accurate and precise, shooting the ball the same way each time and making it into the basket. So what causes some of these things, right? Accurate and precise in the terms of chemistry, right? Your equipment would be well calibrated and you would also have good laboratory practices. Not accurate but precise, you probably have good laboratory practices, but a lot of times this is caused by poor calibration of equipment or some sort of systematic error, right? It might not be your equipment, there might be something wrong in your procedure, but you are following that incorrect procedure very well, right? So this is some systematic error, and this one, if you're not accurate but precise, can usually be accounted for and remedied pretty quickly. Right? Accurate but not precise. There's probably something going wrong with your procedure, your laboratory technique, something like that. Something like all your equipment is good, your procedure is good, something is going wrong in your reaction, or there's some problem with stuff that you're using. And then, of course, not accurate and not precise. Well, that, I don't know, you should probably just give up chemistry at that point and go, I don't know, play basketball or something. So in these two pictures, right, we've got two scales trying to figure out which one is more accurate. Hopefully, you can pause the video and think about this for a second, but even if you don't, hopefully you can see that the one on the right is more accurate. It is delivering information with a greater degree of accuracy, right? It is telling us more about the mass of that particular weight than the one on the left because we have an extra digit with which to gain information. So that's accuracy and precision. But now we're going to get to significant figures. And there are some rules as to what makes a number significant in the first place. So numbers are significant if they provide accurate information. So that means any non-zero digit is a significant figure. So anything that is not a zero is significant. Easy enough, right? Now, that was the one rule for things that are not zeros. There's about 7 rules for zeros. Okay, so the first one, any zero between two non-zero digits, right? 101. All of these digits are significant, which means this has 3 significant digits. This right? These zeros all between two non-zero digits, so this number has 7 significant digits, right? 1, 2, 3, 4, 5, 6, 7. All of those are significant. So then zeros after a decimal point if they are preceded by a non-zero digit, right? So like here, after a decimal point, and they are preceded by non-zero digits. So that means all of these zeros are significant. Now here, in this one, this 0, right, this first one, not significant because there is no non-zero digit preceding it. However, these 3 after, those are significant because they have non-zero digits preceding them, right? So this number over here, 5 significant digits. This one, 6 significant digits, right? We have 1, 2, 3, 4, 5, 6 digits that are significant. And then any 0 to the left of another 0 with a line over or under it, right? So in this case, with 1,000, we have 1, 2, 3 significant digits because this one with the line and anything to the left of it is significant. So that is 3 significant digits. This poor 0 hanging out at the end, insignificant. And here, right, we see our 0 with the line over it. So everything to the left is going to be significant. And these two hanging out over here, not significant, right? So we have 1, 2, 3, 4 significant digits in that one. And then, of course, any 0 to the left of a decimal point, again, if it is preceded by a non-zero digit, right? So the way that we can tell all these zeros are significant is that there's a decimal point there at the end of this line of zeros. And so we have 1, 2, 3, 4, 5, 6 significant digits. Okay, so that is the rules for zeros being significant. Now, when are numbers not significant? When a 0 is to the right of another 0 with a line above or below it, like we saw in the previous page. All right, so this 0, whoops, these zeros, right, they are not significant. When a 0 is after a decimal place without a non-zero digit before it, right? So that means all these zeros here, right? All of these are not significant. This number only has 1, 2, 3, 4 significant digits, right? All those zeros out in front, those are placeholders. They are not significant. Things that do not count toward significant digits or sigfigs when you are doing math. Constants, right? So 6.02 times 10 to the 23rd atoms per mole, Avogadro's number. You do not count any of those digits as significant. They are just hanging out there. It is a constant. That's it. 3.00 times 10 to the 8th meters per second, the speed of light. That is also not counted towards significant digits. Pi, right? If we use 3.14, those do not count towards significant digits. Another thing, fractions or numbers that are part of an equation, like k equals 1/2 mv squared, right? Kinetic energy, 1/2 mv squared, right? That 1/2 does not count towards significant digits for calculations. The circumference of a circle, 2 pi r, right? That 2, not counting towards significant digits. And why am I saying this? Why is this all important? Because now we're about to do math, and we're going to pay attention to significant digits while we do it. So, there are, of course, rules for this. Rules for multiplication and division. When you are multiplying, or it should say dividing instead of diving, when multiplying or diving, your answer can only have as many sigfigs as the number with the least sigfigs in the calculation, right? Which means your answer can only have as many as the least that goes into it, right? So for example, in this calculation, we have two numbers, right? This first one here has 5 significant figures. Our second has 1 significant figure. So when we calculate this out, your calculator may give you an answer that's something like this. However, that answer has many more than 1 significant digit. So what we have to do, we have to round that answer to 30, right? You will notice no decimal point, only 1 significant digit. That is the answer that you have to give for that problem when taking significant digits into consideration. Here, all right, for this one, we have 5 significant digits here, and then we have many more here, right? We have 1, 2, 3, 4, 5, 6, right? 6 significant digits. And you may think, okay, great. Now we're good. 1, 2, 3, 4, 5. Fantastic. Now we have 5 significant digits. We're good. In fact, we don't have to do that. We don't have to add because we had 5. So now, rules for addition and subtraction. So in adding or subtracting, your answer can only have as many digits past the decimal point as your number with the least digits past that goes into the calculation. So I'll let you read that. I'll let you think about it for a second. We'll do some examples, right? So here, right, adding these digits past the decimal, we have 1, 2, 3, 4 places past the decimal in one number, and 1, 2 digits past the decimal in another. Now, when we do this in a calculator, it will probably give us something like this. However, we can only have 2 digits past the decimal in our answer. So we cut it off there. Our answer with respect to significant digits is 21.25, even though our calculator will give us more digits. Here, what do we do, right? No digits past the decimal. Here we've got plenty. Our calculator is going to give us something like this. However, when we take into account significant digits, our answer is going to have to be 0, right? Because this, no digits past the decimal, and here, 4 does not round up. So with respect to significant digits, the answer to that calculation is 0. So significant figures in multi-step calculations. For problems with both multiplication and division and addition and subtraction, always follow PEMDAS. So in this case, right, we would multiply these two together, one because they're in parentheses, right, parentheses, and then multiplication and division, right? So those are the things we do first. So our answer here, right, is going to give us something with 4 significant digits. And then afterwards we do our addition and subtraction, which means we will only be able to have 2 digits past the decimal. And so, right, here we multiply. That gives us our 4 significant digits. Then we subtract, we get this number, and we round up 3.3 2. For problems with multiple steps, follow the rules for each step, right? Individual calculation, carrying only the rounded answer on to any following steps, right? So here, if we are calculating a volume of something and then are going to carry that on to calculate the density of something, right, using our volume, we're going to calculate with length, width, and height, right? We're going to get some answer. We're going to follow the rules for that step and then carry it on to a subsequent step. So our volume, right? Lowest number of significant digits is 2 right there. So we get our answer from multiplying these all together. Then we round to a volume of 32. We then carry that 32 on to our next calculation, which gives us only 2 significant digits, right there. So we get this answer, then we have to round for a final answer of 7.9 grams per mole. The actual density would be 7.874, but we have had to round for that. All right, that's all I've got for significant digits and the calculations of them. We will talk more about this in class.